Good evening, ladies and gentlemen. Let's talk about the area bounded by the graphs of f and g from x equals a to x equals b. Thus far, we've only talked about the area above the x-axis below a particular function from x equals a to x equals b. Today, we're going to focus on the area bounded by two graphs from x equals a to x equals b. And for this particular example, these arbitrary functions, this is the area that we're looking at right here. So I'm going to come up with a formula to find that area. Well, what we're going to do, and we're going to do the same, we're going to start off using the same method, adjusting it a bit, that we found for finding the area above the x-axis below one particular function. And what did we do? We drew a rectangle. So what we're going to do here, we're going to sketch one arbitrary rectangle here. And we're going to note the area of that rectangle. The area of that one rectangle, that's going to equal, well, let's find an x value. Well, let's find an arbitrary x value. Let's look at this dude right here. And all that I know is C is between A and B. And if that is the case, if C is between A and B, then the height of this rectangle, I think it's fairly easy to see that the height of that rectangle is going to be f of C minus g of C. And we know the area of a rectangle is base times height. In this case, it's going to be height times base. And what's our base going to be? And just as we did before, as we developed that other formula that we used for the area above the x below a1 function, we used delta x. So couldn't we say that the base of this rectangle is delta x? I think we could, and I think we would all be comfortable with that. So we have base times height. So the area of this one rectangle is going to be f of c minus g of c. That's the height times delta x. So if I want to find the total area, what I'm going to do, same thing I did before, I'm just going to find the area of, what am I going to do? I'm going to look at the area of multiple rectangles. And here's the picture, here's the graph of a bunch of rectangles. Oh my goodness gracious, I have all of these rectangles. And I have my arbitrary x value between A and B, but I'm going to just let it be, since it's going to vary, since my rectangle could be anywhere, I'm going to let x sub 1 be my x value between A and B. And again, what am I going to do? I'm going to find the area of one rectangle first, which is going to be f of x sub 1 minus g of x sub 1 times dA, which is going to be height times the base. Oh, we want to use delta x because we're not using a very big we're not using a little itty-bitty skinny rectangle yet, because we're only looking at one. But if I want to add up all of those rectangles, which gives me the sum, which gives me the area bounded by that, and I want to sum all of the rectangles, you guessed it, I'm going to use this definite integral symbol, which is going to be the sum of all the rectangles. And all I need is an x value. And instead of using x sub 1, all I want is any x value between A and B. Any x value between A and B, where x is between A and B. And now the bases of the rectangle are so skinny, we're going to call them d of x. And this is going to be the formula. And we know that this is the definite integral from A to B of the quantity f minus g of x dx. And this is the formula. This is the important formula that we're going to use to find the area bounded by two graphs from x equals a to x equals b. And before I go on with an example, I want to go back here a moment. Does it matter? Look at this. Does it matter? I'm going to grab this x-axis. I already moved it for an example. Does it really matter that both of those arbitrary functions are above the x-axis? Does it matter, does the height of that rectangle change if maybe one arbitrary function is above the x-axis and one is below? Or even if both are below the x-axis, does that height ever change? Keep in mind that height has to be positive, and we know dx has to be positive. And in order to drive that point home, let me go here. And I'm going to erase some things here. And I'm going to show you that indeed it does not change. I'm going to pull these guys out of there just for a moment. And I'm going to just do a couple constant functions, if you will. Do a couple constant functions. We'll let that guy be, I don't know, let's let that be y equals 5. And let's do another constant function, if you will. And we'll let that one, keeping with the same notation, let's let that one be y equals 2. And what is this distance here? What is this vertical distance? What is that distance between y equals 5 and y equals 2? Well, that distance, you would think that it's 3. How can I write that? It's going to be 5 minus 2 is equal to 3. So let's look what would happen if I take those constant functions below the x-axis. Let me erase this for a moment. And let's sketch a function down here. We could do that right here if we'd like. Let's just pull these guys out of here for a moment. And again, we can let the top guy be y equals 2. And we'll let this bottom guy be y equals negative 3, if you will. And what I want is this distance right here. What in the world is this distance? What is this vertical distance between y equals 2 and y equals negative 3? It's still going to be, isn't it, 2 minus negative 3, which is 5. I think it is. Because this distance, I have 2 here, I have 3 here. That vertical distance is 5. It's the top minus the bottom. Top minus the bottom. The top graph minus the bottom graph. And again, I could do the same thing. I could pull everything out of here. Let's erase everything. And our last example we'll do, we'll let both of those guys be below the x-axis. And we'll let this rascal here be y equals negative 1. We'll let this guy be y equals negative 4. And what is this vertical distance? What is this vertical distance? What is that distance right here? Well, I think that distance is going to be 3. And how do I get it? Well, that's equal to negative 1 minus negative 4. So no matter what, so back to our original graph, it really doesn't matter if both of the graphs are above the x-axis, if one is below, one is above, or if they're both below, that vertical distance, that height is still going to be f minus g. So it doesn't matter. And we certainly are going to look at several examples like that. So let's go to our very first example. Let's go to a real example here now. So the example is find the area bounded by the graph of negative x squared plus 16 and g of x is equal to 2/3 plus 2 from x equals 1 to x equals 3. And yes, indeed, we are going to use our graphing calculator. So don't get bogged down on coming up with the correct graphs, because we're going to make sure we come up with the correct graphs. We'll use our graphing calculator. Should we be able to graph these without a graphing calculator? By all means, but just for giggles, let's use our graphing calculator. And we have the graph of negative x squared plus 16. And I have the graph of the line 2/3 x plus 2. I want the area bounded by these two graphs from x equals 1 to x equals 3. And it's always a really good idea to go ahead and sketch an arbitrary rectangle. And if you sketch that rectangle, that's going to give you a really good sense. Hey, I need to find the height of that rectangle. I need to find the height of that rectangle there. And what is that? And I'm going to just pull that x sub 1, which is between 1 and 3, that arbitrary x value. The area of that one rectangle is going to be f. F is above g. F is the red, which is above the blue. This is going to be the height. The height is going to be f of x sub 1 minus g of x sub 1 times the base. And we're just going to go ahead and go right to a little itty-bitty skinny base and call it d of x. So, and what do I want to do? If I want to find the entire area bounded by those graphs, what do I want to do? You're darn right. I want to sketch infinitely many rectangles. And what's the height of each rectangle? You guessed it. The height of each rectangle is going to be this f minus g here, times the base, which is gx. And let's substitute the graphs that we actually have. The functions that we have, which is x squared plus 16, that's f, minus 2/3 x plus 2, this is g. Make sure you use parentheses here. Otherwise, you'll get the wrong answer. And we want it from x equals 1 to x equals 3. And keep in mind, we're just going to put an x in because any x varies from 1 to 3. And so we're just going to use f of x and g of x. And what I'm going to do to actually find this, I'm going to use my calculator and put into one of my y equals bars. I'm going to put this rascal right here. I'm going to put that into my y equals bar, and then I'm going to go second calculate, option number 7, lower limit 1, upper limit 3, and that is going to give me the answer of 16 2/3 units squared. Okay, let's go to one more example before we assign some activities or some problems for you to do. And here's our final example. So example 2, find the area bounded by the graphs of f of x, 1/2 x plus 3, and g of x is cosine x. Oh, heaven to Betsy, we have a trigonometric function, a simple trigonometric function, ladies and gentlemen. And I want the area bounded by those two graphs from x equals pi over 3 to x equals 3/2 pi. So let's indeed, what's the first thing we're going to do? Well, the first thing we're going to do is we're going to take our graphing calculator and sketch the area. Sketch the area, ladies and gentlemen, sketch the area. So for any problems that you do at this stage in the game, what you want to do is sketch the area and label your lower bound and your upper bound. We're going from pi over 3 to 3/2 pi. Next step, which you have to have the first step, you have to have the area sketched before you can do what? Before you can sketch a representative rectangle. And what is the height of this rectangle? The height of this rectangle, let's see, what is it? Yes, indeed, the height of this one rectangle is going to be f of x. We're going to pull an arbitrary x value. Is going to be f of x sub 1 minus g of x sub 1 times the base of that rectangle, which is dx. So that's the area of one rectangle right here. Keep in mind, I want to find the area of how many rectangles? Of how many rectangles? Of how many rectangles? You guessed it. Of infinitely many rectangles. And how do I find that? This is where I'm going to use the sigma notation or the definite integration notation. This stands for the sum of infinite rectangles. And what do I want? I want f of x, which is the top function, this 1/2 x plus 3. The bottom function, which is cosine x, and I want that from pi over 3 to 3/2 pi. Make sure that you sketch the area. This is the area that I desired right here. So this is my integration. This is my integral. And I'm going to put this whole creature, this is eludes several students. I'm going to put that whole creature into sum y equals into my graphing calculator. I'm going to use my graphing calculator, the definite integral function. Second, calculate option 7, lower limit pi over 3, upper limit 3/2 pi. 3/2 pi, not 3/2 x. This is going to be 3/2 pi. This is going to be a number. And I put that in my graphing calculator, and it looks like I'm going to get 10.139 units squared. And this is certainly found with my graphing calculator. So that, ladies and gentlemen, is going to give us some good examples, 2 really good examples, and a very good formula where we can actually find the area bounded by 2 graphs from one x value to another x value using our graphing calculators. Good day.